Okay, so I said I wanted to go over some examples or questions um that I didn't get a chance to quiz you guys on your midterms, on your midterm exams. I think this is well, let's go through the signal to start out with, which is since that's the first topic that was covered. I think we did come across a question like this in your midterms, and majority of you, some of you didn't get a chance to actually see the question. I don't know if it was due to time or it was just whatever it was. I know majority of you uh, didn't complete that part of that question or that particular question. So I want to go over it real quick. So at least when you do come across it again in your in an exam or in any kind of workshop or real world scenario environment, you would know how to go about it. Especially if you're going to be building, electronic systems someday uh, to handle, some kind of transmission needs, and it needs to be, you need to incorporate some kind of general encoding techniques into it, and you definitely might want to pay attention to this. Okay, so I do have a signal over here. Um, if you go through the various bits, you will notice that it's actually 1, 2, 3, 4, 5, 6. It's a 6 character message or signal. Okay. And the question I would ask you is, or what I would tell you is, the signal is using some kind of encoding technique. In this case, it's the non-return to zero inverter that was used to encode the signal. So this signal you see over here is actually being encoded with a non-return to zero inverter. And the question that I would ask you is to find the binary representation for that signal, and then the decimal as well as the ASCII, which will give you the actual message that you're looking for. So you got three questions that you might come across. The binary representation of signal based on the signal encoding technique used, the decimal representation of those binaries, as well as the ASCII, which is actually the more or less the message itself. So let's go through this real quick so we can actually decode the message at the end. What I've done is I've started with the initial, uh, a bit sequence for all the characters involved in this signaling. So I have the zeros, the zeros, the zeros for you, but the rest of the bits are missing. So it's all crossed out, and that's where you have to come in and try to figure out what are the corresponding bits after the first bit. So that would help you be able to come up with the either the correct binary or the decimal as well as the ASCII. So let's go through this. If you have your notes in front of you, or I don't know whether you're using your cell phones or your laptops or whatever, you go back to the non-return to zero inverter rules. It states that zeros have a level voltage pulse, and ones comes with a high voltage pulse. They transition when you do have when you have 0 to 1, when you transition from 0 to 1 or 1 to 1. Any other thing else it just stays at the same state that it was on or it was in before any transition or before any corresponding bits kicked in. So with that in mind, let's try to go through the sequence and identify the missing bit. So we have the first bit, which is obviously a low start. So we do have a 0. Now the second one, if the signal went up, it's on a high voltage pulse. So that tells you it has to be a 1 then. So let's change the X back to 1. The next one, it's still on the same state, still at the same state. So that should tell you that based on the rules, you remain on the same state when you're moving from transitioning from 1 to 0 or 0 to 0. Right? That's where you stay at the same state that you were in before. From 0 to 1 or 1 to 1, you have to transition. You have to change the current state. So if the 1 still stays, the signal says that, or the signal that corresponds after the 1 bit is still at the same state, that should tell you that it's actually a 0 then. Because that based on the rules, 1 to 0 or 0 to 0 are the same states that the signal has to be in. Now, from 0 to, if you pay particular attention, the next bit, the next signal has dropped down, has changed state. So if it has changed state, that tells you that it's probably a 1, because you transition from 0 to 1 or 1 to 1. So if the signal drops to a low voltage pulse, then basically that tells you that the next bit has to be a 1. So that's 1 right there. Now, at that 1, we still remain on the same state on this next bit. So that should tell you that that's also going to be what? A 0, right? Because 1 to 0, you stay at the same states that you were in, or 0 to 0. Those are the states that you don't change your transitions, or you don't change your states. You only change your states, which in reference you transition when you do have 0 to 1 or 1 to 1. So let's keep track of that. Are we good? 0 to 0s, no transitioning. So yeah, 0 to 1, you transition. 1 to 1, you transition. But any other thing else, you do not transition. You just remain in the same state. Okay, so now we're moving on to the next bit. There is a transition. We had to move from a low voltage state to a high voltage state. So in other words, that should automatically tell you do have a 1, because we're transitioning from 0 to 1 and 1 to 1, blah, blah, blah. The next bit, or the next signal line, is at the same state again. So the only way it would probably be at the same state based off the not return to 0 inverter would mean that it would have to be a 0 then. That would be the only guess that you'd have, since you have a 1 before that. The next one happens to have changed states. The next bit seems to have changed states. So that should automatically also tell you that you do have a corresponding 1. So because you're moving from 0 to a transition state, that obviously has to be a 1. Okay? And then the next bit is a 0. So the same, you just basically remain at the same state. Now moving on. So we've completed the first character, the first 8-bit character. Now we're moving on to the second 8-bit. We do have its first bit to be 0. Now since this is a continuous, it's actually a message, we have to look at it from that angle. We have to transition, or we have to look at the signal movement from that angle, we're not going to say it's a separate signal or a separate message or a separate character. We're just looking at it from as one bulk message being transmitted. So obviously we continue the transitioning process or applying the same rules that applies to the encoding techniques used. So anyways, from 1 to 0, there was no transition. So we're in the same state. Now, from 0 to the next bit, which you don't know, it still remains in the same state. So that can only happen if you have a 0 bit, because with the non-return to 0, non-return to 0 inverter, there are no transitions from what? 1 to 0 or 0 to 0. Okay? So if the bit before that is a 0, then if there was no transition, and the signal stays at the same state, and obviously its corresponding or the following bit, sequence of bits, has to be a 0 then. So that would be a 0 right there. Now there's a change, there's a transition from a low voltage pulse to a high voltage pulse. And can you help me with that? What will be the next bits then? Hello? Hello?
Hi.
Yeah, so what will be the next bit then?
Yeah.
If you're following for the first 8 bits, what will be the third bit for the second character?
1.
It'd be a 1 because it was a transition. So we transition from what? 0 to 1 or 1 to 1. So if the bit before is a 0 and there was a transition, it must, the only clue you can guess is that it has to be a 1. That's why you transition. What about the next bit? You're in the same state. So what would that be? Anybody? Oh, guys, unmute yourself and answer. Daniel, what's up? Yeah, talk.
It's 0.
A 0. Why is it a 0? Why is it a 0? Why is it a 0?
Because it's on the same level.
Because it's on the same, it's on the same state, or it's at the same state. So it's a 0. What about the next one?
0.
0 again. Why is it 0?
On the same state.
Exactly, we're the same state. So obviously, the following 3 bits are going to have the same, right?
Exactly.
So 0, 0, 0, and of course 0. Now we're on the third character, right? We're on the third character. And on the third character, the second bit, there was a transition from a high voltage pulse to a low voltage pulse. So that means the subsequent bit has to be what? Anybody?
Size 1.
It's 1. There you go. It's 1. Now the next bit has a signal transition from a low voltage pulse state to a high voltage pulse state. So what will be the subsequent bits representation then? What will be this bit here?
It's a 1
Why is it a 1?
because the transition is from 1 to 1 and 0 to 1.
Good. So we have 1 to 1. Now we have another. There was another transition after the 1 to from a high to a low. So what does that mean?
Another 1.
Another 1. Okay, what about the next one?
0.
There's 0 because there was
It doesn't transit from 1
there
to
was
0.
no transition. We're at the same state. So it's a 0. What about the subsequent one?
0.
0. And then
1.
a 1. So you guys are catching on now, right? And then
A 1.
a 1. And obviously a 0, right?
Yes.
Since we were at the same state. Okay, moving on. It's a transition now from a low voltage pulse state to a high voltage pulse. It has to be what?
A 1.
A 1. What about this one? The third
Another
bit.
1.
It's another 1.
0.
At 0.
0.
0.
0.
0.
0.
1.
0.
Okay. And
1.
then a 1. Okay. And obviously a 0, right?
Yes.
Well, now what about this one?
0. 1.
It has to be a 1. It can't be a 0 because there was a transition. What about this one?
A 1.
A 1. There was a transition as well. What about these two, these three here?
Zeros.
There has to be zeros. There you go. Now there's a transition. So what's the
1.
1, right? No transition.
0.
A
0.
0. A 0, obviously. There's a transition. A 1.
1.
A transition.
1.
And
0.
0. A transition.
1.
A 1. No transition. 0.
0.
0. And
1.
and 1. So you got your binary bits. Now, was everybody following? I realized after the third, or the third, character, people started to catch on, right? Most of you were catching on, right?
Yes, sir.
How many of you didn't quite get exactly what happened? I mean, how we got those binary representation of the signal that we have. If you didn't quite get it, let me know so we can go over it again. Daniel has his hands up. What's up, Daniel? Daniel is gone. So everybody's good. Is that what it is? Is that what I'm getting? Everybody good? I'm not getting much interaction from you guys. Are you guys sleeping? You tired from work? What is going on? Daniel, talk. You don't have to put your hands up. Talk. Okay, since I'm not getting much of any, I'm guessing you guys seems to be very conversant with what just what just happened or how we got those binaries. Okay. So
Yes, sir.
okay, so with no questions or comments or complaints, let's move on to the getting the decimals or calculating decimals. So for the first 8, calculating the decimals, it's you guys probably should know by now how to convert. I think I went through that already with you guys, so you can easily get that. The rightmost bit happens to be a 1, so it's 2 raised to the power 0, which is obviously a 1. So there's 1 over here. On the third bit, which is your 2 raised to the power 2, happens to be a 4. So you got 1, 4. So 1 plus 4, which is 5. 5 plus 16, right? What is 5 plus 16? That's 21, right?
Yes, sir.
21, and then we do have 64. So what is 21 plus 64? 85, right? So that's 85, right? So that's 85, and I hope you guys understood how I got the 85. I'm just going by the conversion from binary to decimal using the exponential rules, where if a bit is on, it takes the full value of its sequence. So in this case, the rightmost bit was 1, so obviously it carries 1 as a decimal. The third bit is 1, which carries a 4, which is 2 raised to the power 2. The fifth carries 2 raised to the power 5, right? Which is what? 16, right? And then the seventh bit carries 64, which is 2 raised to the power 6. So you have 64 plus 16 plus 8 plus 4 plus 1, giving us 85. The second character pretty much has all zeros besides the 1, 2, 3, 4, 5, 6, besides the 6th bit, which is 2 raised to the power 5. And that should give you what? What is that? So if that's 32, right? That's 32 right there. This, on the other hand, has got a number of bits switched on. So we're going to have to go ahead and calculate them. So we do have 1 plus 2, which is 3. 3 plus 16, which is what? 19. 19 plus 32. What is 19 plus 32, guys? 19 plus 32. That's 51, right? And then we have 64. So plus 64, which should give you a 115. So you can do the math again. It's 1 plus 2, which is 3. 3 plus 16, which is 19. 19 plus 32 is 51. 51 plus 62 is 115. The fourth character does have only 3 bits switched on. We have 1. We have 32 and 64. So 32 plus, so 64 plus 32 will give you a 96, right? 96 plus 1 is 97. So 97. The fifth character has got a 2, which is 2 raised to the power 1. So there's 2 here. 32 and 64, right? So that's 92 plus 2, which is 94. And then the last character is 1 plus 8, which is 9. 9 plus 32 is 41, right? 41 plus 64, which is 105. 105. So that happens to be your decimal corresponding to the corresponding binaries that we have, the 8-bit sequence binary we have. So now what I have to do is basically go through your ASCII conversion chart and try to figure out what these decimal corresponds to in terms of ASCII. And if I'm not mistaken, 85 is uppercase U. 32 is on the low side, so it has to be a space. Yes, 32 is a space. 115 is a lowercase s on the ASCII. 97 should be 96 is R and S. So that should be A, lowercase a. Which if lowercase a, that's a bit tricky. I think something is, let's go, let me check, let me make sure. So we have the right ASCIIs. Yeah, let's make sure we have the right ASCIIs. I think this and this have a problem. Let me see, let's go. This is 2. So we got 64, 32 plus 2. 64 plus 32 plus 2. So it's 98. We screwed up on that one. It's 98. Yeah, that makes sense. Okay, so that'll be correct now. That means this should be a B. Because if A is lowercase a is 97, then obviously plus 1 should be a B, which is 98. And the last character, which is 105, 105 should be, let me get the ASCII so I don't get you guys. So let's get the ASCIIs. The ASCII conversion chart, where are you? So at least we don't give the wrong message out. Are you guys with me, or everybody's just, watching? You guys paying attention, or you just, watching what's going on? Okay, so this is the ASCII conversion chart. The last bit was 105. Was it 105? Was it 105? 105, yeah, 105. So let's look for 105. 105 is lowercase I. So this is I. lowercase I. So the actual message is you space sabi. You sabi. So do you know? Is that correct? Like pigeon, right? Abi is sabi, right? Hello? Let me cross-reference with the 32. 32 is, yeah, it's a space, SP. The 32 space, that's correct. So there's a space here. So you are typing uppercase U space S-A-B-I, lowercase, S-A-B-I. U space sabi, that happens to be the message. So if you were to decode the signal, this will be the message that that would come out. Capish, folks? Hello?
So we are here.
Yeah, I'm not hearing you guys. When I was going through that, I didn't hear anything.
You muted us, so
We're muted.
Okay, so you guys you figured out how I got this decoded message, right?
Yes.
Everybody did?
But the calculation, yeah, I didn't get it.
The calculation part.
Yes.
Were you in class the first day we went through the conversion?
No, please.
That's pretty. That explains why you're not getting it. So, anyways, if you do have 8-bit sequence in binary, and you want to convert from binary to decimal, there's a simple format which is based on exponentials. The law states that the rightmost any bit that's in a high state or in an on state would take its corresponding exponential full value. And usually, since in computers, we start counting from 0, the first rightmost bit takes the exponential value of 2 raised to the power 0. 2 meaning it's in binary, obviously. And the first rightmost bit starts with a 0 sequence in terms of numbering. The second bit would have 2 raised to the power 1. Third bit with 2 raised to the power 2. Fourth, 2 raised to the power 3. 2 raised to the power 4. 2 raised to the power 5. Power 6, and 2 raised to the power 7. So technically, you're getting 0 to 7, which corresponds to your 8-bit sequence. Okay? So if you understood that concept, stating that when you do have any of those bits in its high state or in an on state, it takes the full value of its exponential value. So in this case, to get the 85, it means that since the first bit is 1, that means it's in an on state, it will take the full value of 2 raised to the power 0, which is 1. 0, on the other hand, it's obviously in an off state, so it can't take the full value. But the third bit has 1. It's in an on state, so it has to take the full value, which is 2 raised to the power 2. So that would give it a 4. So we have 1 plus 4. This right here will be 2 raised to the power 5, which is what? 16. And this over here will be 2 raised to the power 6, which will be 64. So you got 64 plus 16 plus 4 plus 1, and that's 85. So did you get that?
Yes, sir.
The guy that asked the question, you got it now? Or are you still in a limbo? So anyways, if you have the 85, you can just look up your ASCII conversion chart. 85, it's right up somewhere here. And that's uppercase U. So 85 decimal, its ASCII is uppercase U. So that's how we got the uppercase U. 32 corresponds to a space. 32 decimal is actually an ASCII of space, SP, space. When you type the space bar, that's the decimal value of it. And obviously has this binary, which is 001, 0000000. So that's what you see over here, 001 and all zeros. Are we good?
Yes, sir.
Do we have any of the ladies on here too in the class up here? I see an Agnes. Is it Agnes? I see Priscilla. I see Priscilla. Who else? There are a couple of, so just a couple of ladies. How many girls are in the class? The evening students. Y'all are not answering my questions, man. What's up? How many ladies are in the class? Hey, what happened to Ruth? Ruth is not in the evening. Is Ruth in the evening? Yeah, Ruth's part of the evening session, right? As a class rep. Is that correct?
Hello, sir.
Yeah, if I'm asking questions, you guys are unmute yourself and talk.
But it's not allowing us.
Yeah, we couldn't unmute ourselves.
So, yeah.
Allow.
Yeah. You have to allow us to do that.
So you can check the chat. We've been complaining since.
Really? There are chats. I don't know. There are a lot of chats over here.
Yeah.
If you have anything to say, just mute your mic so that the guys asking to say we'll talk. So I see the chats over here. I'm sorry, I wasn't looking at the chats. Okay, so you guys mute yourselves. Yeah, if the guy with the mic will not say anything, who is that? And you say, if you don't have anything to say, just mute the mic. Okay, if you don't have anything to say, mute your mic. So the guys have something to say will do that. Are we good? Hello?
So we can hear you.
Yes. So were there any questions, since you guys said you couldn't unmute yourself, were there any questions as to how we came about with some of these binaries and decimal and ASCIIs? No questions, right? Okay, so there are no questions. Everybody understood this. Everybody got the whatchamacallit. Everybody was with me, right? You're all with me.
Hello, sir.
Yeah.
Sir,
Yes.
I actually joined the lecture a bit late, so I don't seem to understand what you've been teaching all this while. If you can kindly go over it again, please.
Asa, why did you join late? Huh? Mariam, mute your mic if you're not going to say anything. You're getting feedback. Good. So the guy that was asking me about how we got these since he joined late. So we had a signal which was encoded with a no return to zero inverter. And we had to figure out the binary representation of that signal, as well as the decimal and the ASCII, which is the actual message itself. So if you were to go through the signal using the no return to zero inverter, these were the binaries that we came up with based on the rules of the no return to zero inverter, which states that zero starts with a low voltage start or low voltage force. One has to be a high voltage start, and you only transition when you have 0 to 1 or 1 to 1. Any other state, which is say 1 to 0 or 0 to 0, you do not transition. There are no transitions in that respect. So with that said, if you were to go through this, the first bit is a 0, so you do start with this low voltage pulse. The second bit happens to be 1, so it's a high voltage force. The next bit is a 0. By the way, before that, these were all X'd out. It was only the beginning bits that were represented. So the binaries were pretty much they were all X'd out. We X'd out the besides the first bit, the initial bits, the rest were all X'd out. So you were supposed to deduce the binary based off the signal and the encoding technique used. So that's so if you came in late, this would not be you wouldn't see this. It would just be X all out, and you have to figure out how to generate the binary from the signal based on the encoding techniques being used. Okay. So anyway, since we've already gone through that, let's just go up. Let's just follow suit, I guess. So anyways, a 1 high voltage pulse, a 0, so it says you're moving from 1 to 0. There's no transition, so you still remain at the same state. But you do have a 0 to 1, which requires you to change the state or transition. So that's what we had from a high voltage pulse to a low voltage pulse. And since the next bit is a 0, we still remain at the same state because it's the rule states that from 1 to 0 or 0 to 0, there are no transitions. So we still have a low voltage state. And then the next bit happens to be a 1 if you were to follow through very well because there was a transition. So obviously, that should tell you that it has to be a 1. The next bit would definitely have to be a 1 because there's a transition from a low voltage state to a high voltage pulse or state. Okay, and subsequent signal it still remains at the same state, so it has to be a 0 bit corresponding. The next bit it's a 1 because we had a transition from a high voltage state to a low voltage state. So the only way you can get that is if you have a 1. And if you still remain at the same state for the first 2 bit sequence, that should tell you it's supposed to be a 0 binaries. Now you do change state again from a low voltage to a high voltage, so that should automatically tell you that you're obviously going to get a binary 1 for that particular transition. I'm just applying the rule over here for the not return to 0. So the guy that didn't get the came in late, I'm just applying the rule. If you didn't get the rules, then you probably want to go back and read go through the slide on the signal encoding technique. So that would help you understand how these binaries were generated from the signal. Okay. So if you get a chance, just have the slide in front of you, and then pay attention to this signal, and then just match the rules to it. And you will notice that they flow. Okay. So after that, after you get all the binary, now you have to figure out what a decimal is. So for this, you can just use the rules to get them. Okay. The decimal aspect of it is just conversion based on the exponential rule. I hope you were in class that day, on the first day of class, when I went through the, or the second week when we had the discussion on the first topic. I walked you guys through the conversion based off the exponential. So if you didn't catch that either, then let me just go through it again. I feel like I'm repeating myself. I'm getting tired of it. Oh my goodness. Anyways, so the rules for the exponential, it's based off 8-bit sequence. That states that when a bit is in an on state, it will be a 1, and it will take up its full exponential binary representation. So, and since in computers we count from 0, the first bit takes the first 0 exponential, which is 2 raised to the power 0. The subsequent ones will be 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, 2 raised to the power 4, 5, 6, and 7. So out of the 8 bits, you're going to get 0 to 7 with 2 exponentials. Okay, or with 2 as your subscripts, and then your superscripts will be your exponents for the corresponding 0 sequence, or sequence of the numbers that you have, or the bit that you have. So if we do have a 1 here, and it corresponds to 2 raised to the power 6, that should tell you that that's going to be a 64 here. So because 2 raised to the power 6 is 64. This over here, on the other hand, is at the 5th location, or the 5th sequence. So that should be 2 raised to the power 5, which is 16. And this right here is at the 3rd, which is actually 2 raised to the power 2. And that ought to be 4. And obviously 2 raised to the power 0 is a 1. So it's 1 plus 4 plus 16 plus 64, which gives me the 85. So I apply the same rule across the other binaries, and you should be able to get the various decimal values. Okay, and then the rest for the Ascii, you just use your conversion chart to decode the message. So the guy that asked the question, are we good now, or you still not?
Yes, I'm following. Yes.
Great. Everybody good?
Yes, sir.